Uh, Today, we are going to talk about the implementation of a new slow start algorithm inside the Linux kernel. It's a joint work between Wireside, WPI, and the Lexington Christian Academy. I'm Feng, named highlighted. My co-org Jie Chang is sitting there, help me to answer some hard questions. Yeah. So here is the agenda. So the first one is why we are doing this, and I will give a very quick review of the search algorithm, and we do some search parameter analysis for that, why we use this parameter, why we use this value, and we give some performance evaluation result here, and we open to the discussion and the future work. Why we are doing this, as I mentioned earlier, we are working for the satellite. The satellite has very unique RTT. So we have very long pipe and it's fat. So we have extremely large fat long BDP here. So here is one example. So I just give the TCP trace graph. We can see there's a typical TCP flow over our network. So if we disable the high start in this case, we can see the problem with this flow. The first thing is it exits from the slow start too late. It exits with very big loss. That means we overflow the buffer. We have buffer flows there. And because we have very long RTT, the recovery time for us is very long. It's around 7 seconds. So during the 7 second time, we actually have no good put. So we have very low throughput there. After that, we continue working on. That's we can see we enter the TCP congestion avoidance mode around the time 25. That's the issue we are facing right now. If you pay attention to the y-axis, the sequence number, we actually retransmit around the 50 megabytes data in the recovery mode. So that's not very efficient. So the people may ask, why not using the high start? There's another problem with the high start. The high start is broken, at least over our satellite network. For example, that's a RTT graph. After we disable the high start, we are using the cubic over the same link. We can see the problem. At the beginning, we're starting from the baseline RTT. It's around only 600 milliseconds. But after a couple seconds, after a couple packets, the RTT measurement have a large variance. The RTT jumped to around 1 second. At that point, we can see there's no any congestion there. We're only sending around 100 packets or even less packets over the forward link. But we already see the RTT is oscillating. That's a challenging issue for any delay-based congestion control algorithm. Also, it's challenging, very challenging for the high start. High start doesn't work very well. Here is our old result. This graph is just say how long we need downloading a given size file. For example, if we're downloading the 50 megabytes file, it may take around 12 to 13 seconds without the high start. But if we enable the high start, we can see the high start may take around 25 seconds. So that we have the problem here. If we disable the high start, we're ending with the buffer bloat. If we enable the high start, the TCP slow start exits prematurely, and we have very low link utilization over the satellite link. So that's why we are doing this. We try to find a new slow start algorithm which can exit at the right point, avoid any buffer bloat. So next, we are going to talk about the slow start. Let's recall how slow start works. At the beginning of the TCP flow, you are going to send in a amount of data, initial congestion window size data. You send us that data onto the link. But when you're going to know it's delivered, it's 1 RTT later. After 1 RTT, you receive the ACK from the return link. you know this data is delivered. At this point, the sender will double its congestion window size and put more data onto the link and keep going. So after one more RTT, the ACK tell you this amount of data has been delivered, and keep going on until we reach the capacity, which is the congestion point. At this time, since we are just right the right capacity, we still get enough ACK. We know this amount of data is delivered. For the next RTT, the sender still double its congestion window size. Then we have trouble here. So we could not get enough ACK. So we know it makes time to exit, but sometimes that's the thing. We put the send curve to the delivery curve together. We can see that's what's happening here. At the initial, it will double. So we always can infer the number of bytes sent based on the previous delivered bytes. So we keep going like that until we reach the capacity. At this point, we may not send in enough data anymore. So we may have a chance to know its congestion point. So as I mentioned earlier, so estimate the send packet can know based on the previous delivery packet before you reach the capacity, reach the congestion point. And if we take that, we can calculate the difference between this, how much data you already put on the link and how much data you received in this cycle. Then you can know the difference. Then we can come up with the normalized difference so that we can calculate the threshold. If we are greater than some threshold, we are going to exit from slow start. The behavior between the traditional loss-based TCP flow for the slow start is we are not looking for the loss. We are looking for the normalized difference between send and receiving. So that is a normalized, the typical TCP flow. We can see it's a when it hits a loss, you reduce the congestion window size and into the congestion avoidance mode and carry on. For the search, when we increase the congestion window size, we calculate the normalized difference. Until the normalized difference greater than given threshold, we exit from the slow start. And ideally, we go to the congestion avoidance mode and have a higher link utilization. The challenging part here is we have RTT with a large variance. So only using one RTT, it may not be enough to calculate this. And another reason is sometimes the RTT variation is not from the forward link. It may come from the uplink, we call the return link. And one thing ideally is we can keep tracking each ACK, the deliver bytes and the sender bytes. We can track based on each ACK, but it is not memory efficient. It may using a lot of memory. We cannot store all the history of each ACK into the all the history of each ACK in the memory for each socket. That's too much. So we come up with the idea, we give a larger window. It's long enough to cover all the RTT variants, and we may need act quickly. So we may divide the larger window into small bins, we call bins. So we can have multiple bins in one observation window to do this. So we shift the bins, then just like do the window sum, so we can calculate the delivery bytes in the given window and compare with expected sending bytes. So that's a whole idea. Here is the algorithm itself. It's a very simple algorithm. It's not fancy. It's only around 100 line code total. The beginning of the part is the stack variable. So we use that as a module variable to do the configuration. The second part is a per flow variable. So each flow has its own variable. So it's based on the RTT to calculate the bin duration and the bin size. And the whole algorithm is based on ACK. When ACK arrives, we do the handling. If it's time to update the bin information, we go inside the if statement and we check the index and we do the calculation to see the factor. So other part is the helper function. We update the bin, we put there, and we do the summation. It's just like the typical window sum. So we do the window sum for which the delivery bytes and do the window sum for the previous RTT previous cycle. So that RTT do another window sum. So we calculate the factor and we do the thresh comparison at line 21. So if the calculate the normalized difference larger than the threshold, we exit from the slow start. We set the slow start threshold to current 7 and exit. So the challenging part here is we need to decide the window size, how large the window is, and we need to decide how many bins we want. And we need to decide the first exit threshold. I start from the first one, how large is the window? The window should be large enough to have the meaning, to capture the meaningful the link variation, the RTT changes. And it also should be small as possible. You can make a decision quickly when you reach the link capacity. We use the faster Fourier transform. We can convert the RTT in the time series into the frequency domain. So we can do that. After we do that, we found it's pretty constant with the different link types. For example, over the geo is a 3.3, on the layer is almost the same, and the Wi-Fi is a little bit larger, and LTE is smaller. So we choose the 3.5 as default and make this parameter configurable if we need further tuning. And the number of bins, that's almost a similar one. Is if you have more bins, you have more fidelity to get the delivery bytes, but it's impossible to have variable for each ACK. So we have to choose some bins to provide the delivery bytes information. This we don't have very good approach, but we run a lot of experiments. So in this paper, we talk about the number of bins selection. We choose the 10 bins as a default. We found it's very efficient. It has nearly same performance as multiple bins up to 50 bins. And it also has very low convergence time. So at a very short time, we can minimize the early exit. So when we close to the maximum capacity. The last one is the access threshold. So access threshold is we need choosing. We determine when we should exit from the slow start. Based on the analysis, it should be somewhere between 0 and 0.5. If you have infinity queue, you will reach when you reach the congestion point, that will be 0.5. If you don't have any drop, you don't have ACK timeout, you don't have retransmission. In this case, you will have the value 0.5. But if you don't, before you reach the capacity, the normalized difference should be 0. So we choose after turns of evaluation and the experiment, we choose 0.5 to detect congestion. In this way, we can detect congestion in less than 2 RTT. Here comes with the performance evaluation. We have 2 performance evaluation in this talk. So first one is the geo. So that's the geo setup. It's a typical geo setup. We have the CPE, it's a client sitting in the WPI campus, and we connect with the WireSat satellite through the UT modem and go back to the ground station. Through the internet, we go to the AWS cloud. So we are using the EC2 server as our server, EC2 server as server. So one thing I want to mention is for the ISP, the WireSat in this case, we have the AQM. We have very large buffer per flow. It's around 36 meg. After you're reaching 50% capacity, you're starting random dropping. Here is how the search behaved compared with the cubic with high start without high start. This graph is pretty busy. So the first row is the cubic with high start. The first graph is the bytes in flight. All this graph generating with the T-Shark with PCAP. The second graph is the RTT graph. The third one is throughput and goodput calculation. The last one is retransmission. To have a better graph, we actually put the retransmission packet in 10 millisecond bin, so that's easier to see on the graph. So the second row is the cubic without high start. We can see the cubic without high start, we can easily pump around 70 megabytes data into the link, and it can reach very high capacity, but RTD goes crazy, it's up to around 7 seconds. And the one thing we need to mention is the retransmission. After you have the packet loss, we have a lot of retransmission packet happen. So the overall output it may not be very good. The last one is the search. The search we can see is exit around the time 15. Then the RTT goes higher because we have a lot of data inside the ISP server. And one thing is we almost have no loss. We only have a couple packets disorder in this case. In this slide, the graph on the left-hand side is the same graph I take from previous slide. I only keep the bytes in flight and the retransmission. And on the right-hand side is based on the special kernel. We do some print key to generate the log for the search, for the analysis. So we can see how the normalized difference changes during the connection, during a slow start. At the time 12, between time 12 and time 14, the slow start, the normalized difference reach the threshold. It exits from the slow start. And the bottom graph is busy. So what x-axis is the time, y-axis is the congestion window size. It's a report from the kernel. And on the y2, the y-axis on the left, on the right is the state, the TCP state. So we can see that we have open, disorder, congestion, window reduction, and recovery and loss. In this case, the loss is caused by the disorder. We have duplex ACK here. So we have multiple ACK with the same sequence, with the same number, and we have the disorder, and we do the quick retransmission. So in this case, we can see search works pretty well over the satellite link. In addition to the GeoLink, we also do some experiment in the WPI Wi-Fi network. We choose Wi-Fi network is just because Wi-Fi network has the variable capacity. It's very hard to decide when is exit time. So we show this here. The whole experiment is running in the WPI campus. So we can see that we have the client connect with WPI access point, then through the internet, go back to the WPI server on the LAN. So we compare, since we compare only the slow start performance, we only run the iPerf for 3 seconds. That's long enough for the for all the TCP congestion control get out from a slow start. We choose 4 different CCA and different from previous study. We put the BBR here and the search cubic with high start and without high start. We repeat it 200 times in this time for the 24-hour window. Here is something we want to talk is from the Wi-Fi network is a strong correlation between the throughput and RSSI receive the signal strength indicator, but it's not all the same time. We have some low throughput case in our preliminary study. We found is at some location, even the RSI is pretty good. We have very low throughput. We think it's due to the shared nature and the Wi-Fi link. We may have high noise at that point. So for this study, we only choose 2 locations we marked as red in this slide. One we think is good, the one with a higher RSSI, we think the strong location, and one with the lower RSI is the weak location. This graph is all the tests we run on these 2 locations. We have 2 CDS curve here. It's a throughput on the x-axis and the cumulative distributed function here. So we can see the median is apart around 100 megabytes. So medium throughput is much higher than at the strong location than the weak location. Here is the main result. We have 2 graphs here. The graph is still download, how long to download a given size file. So the x-axis is the download size, y-axis is the time. The difference is in this graph, we mark when we exit the slow start using the horizontal line. So that's the color match is congestion control configuration. We have 2 cubics here. We can see for this graph, lower is better. So lower means you're downloading the same amount of data with less time. So we can see the BBR did pretty well on the Wi-Fi network with the BBR at a strong and a weak location, and high start on did pretty bad there, and the search even did better than BBR at a strong location. And we could not tell difference in the weak location, but if we look the exit time of the slow start, the search is exit almost at the right time. This graph is compare the slow start exit time. Visually, that's easier. The y-axis is when we exit from the slow start. Axis is the 4 different configuration. We can see when the high start off, we exit the slow start pretty late. We're causing a lot of buffer bloat. And when enable the high start, we exit the slow start almost immediately. So in 1 RTT. And the BBR exits a little later and search at roughly same time as the BBR. As the weak condition, almost the same story. BBR exits a little late than search, but they have similar throughput. Retransmission. So we know when we turn off the high start, we exit from a slow start too late. We call it the bubble bloat. It also happens on the Wi-Fi network. So we can see we have a lot of retransmission packet over the link. And at the weak point, because we did not send too much, the retransmission number is lower, but we have the same story. If we disable the high start, we will result a lot of retransmission, and the BBR version 1 and the search almost performed similar on this in this condition. As I mentioned earlier, this work is still work in progress. We are still doing a lot of testing, and here is the information for this project. On the top is the central hub for this project. Then we have the Linux module implementation. We mainly development this on the 5 series kernel, but we do some code change in the 6.10 RC2 kernel. We test this on the 6.10 kernel also. And beyond that, in addition to the Linux implementation, we also attempt to put this onto the Quick. As we all know that Quick almost take exactly the same congestion control mechanism from the TCP. So they have the similar issue over the links, especially over the geo links. So we have the Quick implementation based on the H2O quickly. So we publish the code review there. So if you have time, please review the change and put some comments there. In addition to that, we also plan to attend the IETF 120 for next week in Vancouver. So welcome to join the discussion there. And we're looking for the comments on algorithm, design, implementation, performance evaluation, and we plan to do more evaluation over different link type even more. So for example, data center, we didn't touch right now. The future work, so that's near future, we try to have more iteration and we try to do upstream also. So we just get into the process to know how to do the upstream and how to do the code review. We may need some help to improve the code quality also. So pretty free to jump on. And if possible, we want to cooperate with BBR to change the BBR probing phase. At this point, only 2 congestion control algorithms may work on the GeoLink. One is search, cubic with search. Another one is the BBR, because BBR is rate-based approach. It's very similar. The conclusion here is we all know high start doesn't work very well in almost all link types. We need some fix for the high start. The high start code doesn't change for around 15 years already. So it's time to fix the high start. The search is a potential to do this. We try to use search to access the store start after reaching the maximum sending rate and minimize the packet loss, do not overflow the buffer and reach the. In our evaluation, we reach a comparable performance with the BBR and TCP without high start in terms of the throughput. So, thanks for the attention. That's the last slide. So, question.
I have a question. Great talk, thank you. You have a question about high start. Have you considered using high start plus plus? Because it's supposed to solve all these issues you have with high start.
High start plus plus is a very good candidate, but the thing here is for the GeoLink, I don't think it will work. The thing is, it's still delay based. It's very challenging for them. I think they designed the high start plus plus not for this long RTT and this large RTT variation. Another thing is we try to find the very good high start plus plus source code, but we don't have the open source one. We plan to put one Windows server there when to run testing from there.
So I think Quick has support for high start plus plus.
Quickly doesn't. We only
I did a high start plus plus.
Okay, that's a good information.
Like Eric, I can give you a little bit of a comment. So high start plus plus is slightly better because when it exits the initial slow start, it actually go to the second slow start phase, and then it could actually do better. So that might be okay for some of the wireless network, but in geo cases, it's still like not really consuming all the bandwidth available quickly. So this is more like we were actually searching for a better way to approach this, and when we actually look at also BBR is taking like it's actually looking at 3 consecutive RTT to actually make an exit decision. And then we actually found that by using this method, we could actually make an exit decision in 2 RTTs. So, and it's more robust in all variable RTT case. So that's why we think it's the main contribution of this work is actually make the slow start exit more robust.
Yeah, I think a partial question you already answered. The question I want to ask is like, do you guys have tried, right? So put your algorithm into BBR, right, to compare how is the performance, because on the algorithm side, so to me it's a little bit similar in that case, right? So it's like the BBR takes 3 RTT to evaluate, right? So it go to the plateau of the throughput, then decide the threshold. So yeah, so if you I don't see any comparison on your presentation from that side. So
compare with the BBR, we don't have that in this talk. We are still working on that. We have a lot of data to processing right now. Yes, we think we complete the testing with BBR on the Wi-Fi, but we didn't do that on the Geolink.
That will be in our next measurement paper.
Yeah. Anyway, in those Wi-Fi WAN case, like the BBR kind of more gain more population than the cubicle anyway. So if you can combine both, to see.
Cut you off short here. I think.
Yes, thank you.
Can we the remote question? I think it's several remote questions. Who's asking? Is somebody remote asking?
Sure, I had a couple questions. Can you guys hear me?
Make it quick.
Sure.
Make it quick, please.
Okay, so I'll just make them as points then. So one thing to keep in mind would be application limited traffic, which would reduce the delivery rate that you're seeing and could spuriously cause the algorithm to exit slow start. You might want to sort of check for that and not exit if it's application limited. Another question would be the memory overhead. It seems like it's about 25 bins times, say, 4 bins, sort of 4 bytes per bin, so maybe 100 bytes, which might double the memory overhead of congestion control. Something to see if I wonder if there's a way to reduce the memory overhead.
Yes, so memory overhead, we are looking into it. Right now we are using 10 bins, but we may be able to actually reduce it. So I mean, that's one thing. What was the first question? The first question was
just application limited behavior would be something to
okay,
to
so I mean, so the job of the initial slow start exit is to figure out what is the SS threshold, right? So the thing is, once SS threshold is actually figured out, then there is no need to actually do this. So in application limited case, the thing is, what we are doing is we are actually resetting. If the new is application limited and then it actually restart, then we don't actually make an exit decision. So so we don't actually harm we don't actually cause the all the exit in this case as well.
I know the person didn't identify themselves, but that was Neil, I think. Yeah. Neil?
Yeah, sorry about that. That was me. Yeah.
Okay. And we should probably be putting them on the screen next time. Okay, thank you guys. We're gonna wrap it up here.